So the final is cumulative. So let's go back and talk about beginning things. And we can sort of talk today about the things from throughout the class that I personally find the most important and think that you should definitely know. All right. So we started way back at the beginning with a definition of a fluid. What is a fluid? According to the technical definition. Anyone remember? What?
Anything that exhibits a shear rate instead of a anything that exhibits a shear rate.
It continuously deforms underneath a shear rate or shear pressure.
Shear stress, which
that's what I was going for.
Yeah, and a pressure is a stress, so yes. And of course, shear stress is related to shear rate. So shear viscous stress for a Newtonian fluid. So dV dy is the rate of change in the velocity as you go down the velocity profile, essentially, in most cases. And that is, though there can be shear stresses going in various different directions, and that's what we learned from the Navier-Stokes equation. So this is the shear rate. This is the shear stress. This equation, sometimes called Newton's law of viscosity. And it shows us that the more viscous something is, the harder it is to deform it. So that to get the same shear rate, you have to apply a bigger shear stress. That was way back at the beginning. We also learned just some general things about fluid properties. So density, for example. What tends to make a fluid more dense? Higher temperatures or lower temperatures?
Lower temperatures.
Lower temperatures? What about pressure?
Wait, doesn't the density depend on if it's like a liquid or a gas? Because if it's higher,
of course it depends on that. Yeah, of course. It depends on whether it's a liquid or a gas, and it will depend on the intermolecular packing, basically. So for example, a gas, of course, is going to have much lower density than a liquid. And then when you are a liquid, then the density could depend on how the molecules pack together. And then it can also depend on the molecular weight of the molecule. But as far as pressure and temperature goes, a lower pressure, what would that lead to? Lower or higher density?
A lower pressure would lead to a lower density.
Yep. So this is just in general. So for any given fluid, you would see this relationship. So then different fluids will have different densities in between them. And then viscosity. So a lower temperature, what will that do to the viscosity of a fluid?
Increase.
CJ?
Yeah, so lower temperature would increase viscosity.
Okay, so actually it depends on whether it's a liquid or a gas. So in this case, in the case of viscosity, the direction of the relationship changes. So that's a little, I'm not going to call it a trick because it's just how reality is. But so for a liquid, so a liquid, when we have a lower temperature, you can imagine that if you put like honey in a microwave, it's going to get thinner and runnier, right? Has anyone done that before? So that means for a liquid, higher temperature makes it less viscous, and a lower temperature makes it more viscous. You can think of that as the higher temperature, the molecules slide over each other easier, the lower temperature they don't. But then for a gas, a lower temperature actually makes it less viscous, and a higher temperature makes it more viscous. And we can think of that as at the higher temperature, the gas atoms are more likely to run into each other and interact with each other, which means they're more likely to grab onto each other and be more viscous. So for gas, lower temperature, more viscous. And then there's not really a very significant relationship between viscosity and pressure. I mean, there likely is some, but it will be much, much less significant than the relationship with temperature and the way pressure changes density. Okay.
Yeah, that's the same holds true for density, right? That the pressure density relationship is less than the temperature density relationship.
Yes, that is true. Well, I guess it depends, because for an ideal gas, for example, and we just always treat gases as ideal generally in this class, that's the density, right? And so for an ideal gas, the pressure and the temperature both contribute. I'm not sure whether you would call one of those contributing less than the other one. So for a gas, it's about the same. For a liquid, the temperature is going to be a much more significant change in the pressure. So it is true that for a liquid, temperature is going to change density much more than pressure will. For a gas, they both affect it. Which leads us to talk about compressibility. So more compressible means rho changes more with P. So so different fluids will be more easier or less easy to compress because their density will change more or less with change in pressure. And what's more compressible, liquids or gases?
Gases.
Gases, yep, because you can take a box of gas and squeeze it small, whereas it would be harder to do that with a liquid. So we generally treat liquids as incompressible, meaning constant density even when P changes. So we ignore pretty much all the time changes in density in gases. And then we treat gases as incompressible for smallish pressure differences. So smallish pressure differences, it's a somewhat subjective way of doing it, but most of the time, there's, for example, in all these, most of the pipe flow problems we do, most Bernoulli operation problems we do, we just treat gas as an incompressible, which means its density is also going to stay the same with pressure. Sometimes when we treat a gas as compressible is again when there's a really big pressure change, so you have a pressurized tank and then you let the gas out, or there's a long enough pipeline that there's going to be enough pressure loss that there will be a big pressure change, or if it is going very fast. And the rule of thumb there is above Mach 0.3, we treat gases as compressible when they're flowing. Alrighty.
Just a quick question. So do those rules also apply to liquids like the long pipe and fast flow?
No, not really. We pretty much never treat liquids as compressible. And it is true. So when we did the compressible flow class, we didn't spend a lot of time on this, but at one point I showed you the speed of sound in water versus in air. So the speed of sound in air at 20 C is about 340 meters per second. And the speed of sound of water in air is like 1200 meters per second. Something like that. I'm going to Google that. Anyway, so and what this tells us is that you would have to go much, much faster for a liquid to act as compressible as a gas does. 1500 meters per second, just Google that. Okay, so that means that you'd have to go 5 times as fast as air does in order to treat this as compressible. And pretty much nothing in water travels that fast. I once looked up, the maximum speeds of submarines, and they're way less than that. And so you just don't really get compressible flow in water. And then it would also need a really, really, really huge pressure change that we just don't really see very often at all in order for water's density to change significantly. Okay. So for liquids, we pretty much just always treat them as incompressible. There might be some people doing research where they're doing very fine modeling where they have to take into account, the bulk modulus of the liquid, but that is not anything we do. Okay.
I just had a quick question about the shear stress. That negative sign, does that just mean it's in the opposite direction of the flow?
It does not mean it's in the opposite direction of the flow necessarily. It means it's in the opposite direction of the shear rate, which a lot of times we're just interested in sort of the absolute value of the stress, and we kind of ignore that. But that's there in order to tell you that, like, okay, imagine 2 plates. One of them is moving at you, right? And so, and then here's the velocity profile like this. That, right? So if the top one is moving to the right, then we know that the shear stress, okay, and so in this case, the velocity profile would be U is equal to big U over H, which is the distance between them. That's just always what it is for those two plates. And it's U is positive because it is going from here to here. And so what that negative would tell you is that, yeah, so in that case, right here, as you move away from this wall, the velocity is going down, right? As you move away from the wall. So the change in velocity would be negative. And right there, the shear stress on the fluid would be pointing that way because the shear stress is pulling to the right on the fluid, right? And then down here at this wall, the shear stress on the fluid would point that way because that wall at the bottom is pulling the fluid to the left because that wall at the bottom is being still. So the wall at the bottom pulls the fluid back that way. The wall at the top pulls the fluid to the right. So at the top, as we go down, the velocity is getting smaller, so you would have a negative shear rate. And so therefore, the shear stress on the fluid is positive, pulling it that way. And then on the bottom, as you go up, as you go in that direction, the velocity is getting bigger, so there's a positive shear rate, and so the shear stress is pointing to the left and would be negative. So I put the negative in there, but it actually sort of depends on what the direction of what the sign of the shear rate would be in the direction you're interested in. But most of the time, or a lot of the time, we're only interested in the magnitude of this. So for example, I could give you the velocity profile in between these plates, or maybe give you like the one we derived from the exam, and I could say, find the force on the top plate, right? So if I gave you a velocity profile in between these, and it was some complicated equation, and I said, so like that one, the one on the exam, and I told you find the force required to pull that top rate at a constant speed, what could you do?
You find the shear stress and multiply it by the area.
Yep, you would find the shear stress. So you would take the derivative of the velocity profile there, and you would find what it is at the wall. And so you would take the derivative of the velocity profile to find the shear rate, and then you would multiply it by the viscosity, and that would give you the shear stress, and then you would multiply it by the area of that plate, and that would give you a force. And what that would be is the force that you would need. So you would need to pull the fluid or the plate forward at that force, and the fluid will pull back with the same force. So most of the, as I said, I put the negative in there because it will handle shear stress going in being a vector and going in different directions, like in Navier-Stokes. But most of the time, in the kind of problems I have you do, I just think through logically what direction the stresses should be pointing. Okay.
Can I ask a question about that? So that confused me because isn't dv dy always in this scenario that you drew, isn't it always positive? So wouldn't, like, I don't understand how it could switch directions.
Yeah, that is That is a good point, which is why a lot of, your book always puts the negative in there. Some just give you the absolute value like this. direction is going to be determined by the direction of the shear rate as you go through the fluid, is just the easiest way to think about it. Sorry, I'm not sure that was a great answer, but okay. All right, that's compressibility. Other sort of basic things is we learned about laminar versus turbulent flow. I feel like this is something that has continued to be relevant through the whole class. So you all remember it. You all remember that laminar flow flows in layers, and turbulent flow does not. And you know that what kind of flows are more likely to be laminar?
That would be like lower Reynolds number. So if you have a smaller diameter, or if you have a higher viscosity, things like that would make it more likely to be laminar.
Yeah.
Or slower.
Oh, by the way, I was just gonna say about the sign of the shear stress. So it is true that the fluid right here at the wall is going to be pulled left on the wall, but it's also going to be pulled to the right by the fluid on top of it. So it would be positive all through here, and that the fluid on top is just going to keep pulling the fluid below it to the right. So it would be positive all through there. Okay. And then, of course, the other layer of fluid pulls the opposite direction because of Newtonian laws. Anyway, laminar, turbulent. The more viscous it is, and the slower it is, and the smaller it is, the more likely it is to be laminar, which we can also see by looking at the Reynolds number, rho v d over mu. D is some length scale, which means in a pipe, it's the diameter of the pipe. If we're talking about the flow over a car or something, it could be the length of the car. So the appropriate length you would use depends on the situation, but in general, the Reynolds number tells us how laminar or turbulent something is acting. Lower Reynolds number means more laminar, higher Reynolds number means more turbulent, and we look at it and we see, okay, the faster it goes, the more turbulent it is. The bigger it is, the more turbulent it is, and the less viscous it is, the more turbulent it is. Also, the more dense it is, but usually that's not the difference in densities that we're talking about. Very often does not make a big difference in this. We don't talk about it a lot when it comes to laminar versus turbulent, but it is in there because the more dense a fluid has, the more inertia it has. And so the more turbulent it's going to act. Okay.
Question.
I'm going to open up the chat room window.
What, besides the like 2300 for circular pipes, and I think there was some critical flow for, oh yeah, power law fluids. Is there any other like transitions that we should know of?
That you should know about. Okay, so there's a different one for flow over a flat plate, but I don't remember it. So I'm not sure I would expect you to remember it. But what you're saying is that's important for everyone to know is that critical Reynolds number tells us where laminar becomes turbulent. Okay, so we define a critical Reynolds number and we say that's where it becomes turbulent. And in reality, there's usually a transition region where it's kind of both or could be one or the other. And it depends on situation. So conceptually, that's the thing to remember is that what Reynolds number signals the transition from laminar to turbulent depends on the situation. And the ones I would expect you to know and to have, and that I would either have you remember or have down in your notes is Newtonian flow in a round pipe. RE critical is about 2300. It'll be fully turbulent around 4000. And then for a power law fluid, also in a power law fluid in a round pipe, RE critical will depend on I'm gonna open up actually I'm just gonna open up the power law fluid lecture in order to get what that is. And you all did the pipe viscometer experiment in your fluids walk-in lab, no? I assume that you did that. Were you? Okay. RE crit for power law depends on this. Like that. Which is usually going to be around 2300. All right. And you can see that if N is 1, like in a Newtonian fluid,
We can't see your screen.
that's going to be 2200 plus 100, it'll be 2300. Yes, what?
We can't see your screen, or at least I can't. I don't know if other people can.
Oh, cannot see my screen. Oh, that's because I opened up. There we go. I opened up the PowerPoint in front of this, and that confused and frightened Zoom. Okay. Yes. So this is for a power law fluid in a round pipe. It's the only other critical Reynolds number I'd expect you to have written down anywhere. It will usually be around 2300-ish. For a Newtonian fluid, N is 1, and so it becomes 2300, just what we're talking about. And I guess this is as good a time as any to go over non-Newtonian fluids. So let's do that. Okay. So what's the definition? I'd like you to know the definition of a non-Newtonian fluid. And what is that, somebody?
A fluid whose viscosity changes as shear stress changes.
Mm-hmm. Yep. Viscosity changes with, I'm going to say with shear rate because mostly when you define these things, that's how you define it, but they're kind of the same thing because when you apply a shear stress, it will create a shear rate and that will change the viscosity. Oh, and what kind of fluids are more likely to be non-Newtonian?
It's like mixtures where they have like particles that are suspended in some kind of liquid phase.
Yeah, often mixtures, stuff inside a liquid. So could be particles, it could really long molecules. things like that. Those are very common. So stuff that's non-Newtonian is often a liquid with some stuff in it, because that stuff is gonna rub together and press together and tangle with each other and create more complicated relationships between the viscosity and the stress and the strain. So what are some examples of non-Newtonian fluids?
Shear thickening.
Okay, so shear thickening is a kind of fluid. So types of non-Newtonian. So shear thickening, which we sometimes call dilettante. Shear thinning, which you sometimes call pseudoplastic. And I would like you to remember those names, dilettante and pseudoplastic, because those are words you might actually hear when people are talking about it. Even though I prefer the words shear thickening and shear thinning, because those names tell you what it does pretty obviously. So a shear thickening fluid would be one where you apply a shear stress and it gets thicker, and a shear thinning is you apply a shear stress and it gets thinner. What's an example of a shear thickening fluid?
Cornstarch.
Cornstarch and water.
Cornstarch and water is the classic. And it is easy to make, and also it is easy to make, and the shear thickening fluids, I think, are less intuitive to us. So if you, say, Google YouTube videos of non-Newtonian fluids, you will probably get a lot of cornstarch and water. And you can see all those neat things, like if you run fast enough across a pool of cornstarch and water, you won't sink, because your foot goes down, it creates a stress, it gets thicker, and so you don't sink in very far. So if you run real fast, you can cross it. I've seen someone ride a bike over a pool of cornstarch and water. Okay, things like that. What are some shear thinning? There's probably more examples that we're familiar with that feel kind of intuitive to us. So what's some examples of shear thinning?
Ketchup would be one.
Connor, what did you say?
I said ketchup.
Ketchup. I like ketchup because everyone, literally everyone, has squeezed the ketchup bottle then to make it run, right? So you apply the stress, you squeeze it, it goes. Ketchup. Blood is shear thinning. Peanut butter. Paint is okay. A lot of polymers. Polymer melts. Plastics. So the shear thickening, if we think about what's happening with the molecules, the theory is that you squeeze it and those molecules and things sort of push together, whereas with the shear thickening, the theory is that you squeeze it and the molecules become aligned and just slide past each other. Okay? And you can see these are all liquid with stuff in it, like we were talking about. Blood has cells in it. Ketchup has tomato cells in it. Things like that. So shear thickening and shear thinning are probably the most common type. There's also time-dependent ones. So these names that they have, all right, I would write them down. I was going to say they seem a bit more obscure to me, these names, but yeah, I would write them down probably, because I want you to know that some non-Newtonian fluids, they change with time. So you put a shear stress on something, and then it will change over time. So thixotropic get thinner over time. This is also like ketchup. You put ketchup bottle upside down, you're applying a small shear stress to it, and then over time will get thinner. That's why sometimes you just set the bottle down for like a minute and then you do it. And rheopectic gets thicker over time. I think printer ink is the only example I can find when I look for this. Though also lots of mud will end up acting in non-Newtonian ways, and all mud is different. So, and then we also talked about Bingham Plastics. I feel like this is the most important kind to know about besides just thinning and thickening. Bingham Plastics. Does anyone remember what a Bingham plastic is?
It has a certain yield stress, so it basically behaves like a solid until you kind of break it apart, and then it flows like a liquid. So it'd be something like toothpaste.
Yep. Like toothpaste. And toothpaste is just a perfect example because everyone knows how toothpaste works.
After it reaches the yield stress and behaves like a fluid, the viscosity stays constant, right?
Yep, that is how it is. So if we were to look at like the stress versus strain, I'm saying dV dy here, but the coordinates could be different. So for a Newtonian fluid, it would just look like this. It's just a line. And then a Bingham plastic, it just looks like this.
Does not fall at all under that category?
Does what?
Does peanut butter not fall at all under that category?
You know what? It probably does. I don't know. I would look that up. Because you're right that, and I bet peanut butter has some time-dependent stuff too, because it looks pretty solid, right? And if you can turn it upside down,
that's what I was thinking about.
So it might be. It could be. I would look that up. That's an interesting question. And yeah, there probably are fluids that have a yield stress and then they act not as a straight line like that. I bet there is. I don't know the name of them or any examples, but I bet there are some. And the theory behind why Bingham plastics act like this is that they have a bit of a crystalline structure like a solid, but then when you apply enough stress to them, that structure breaks down and they can flow. All sorts of things. And we learned about one model of non-Newtonian fluids in particular. We learned about power law fluids, which are fluids that can be described by like that. That's why they're called the power law fluids, because the rheology is described with this equation with a power. Also, I do want to stress to you that I phrased it like that on purpose. It can be described by this because these non-Newtonian fluids can work in various kinds of ways. And so if this model works good enough for this fluid for our purposes, then you call it a power law fluid. And it describes shear thinning and thickening. So that's what it does there. And less than 1, is that thinning or thickening?
Thinning?
That would be thinning. And greater than 1, thickening. Like that. And if n is 1, it's just Newtonian. And so we learned about these both because if you were to actually encounter a non-Newtonian fluid in your job, it would probably be, it's most likely to be thinning or thickening and to be able to be described by a power law. And then also you did a lab in your lab class about power law fluids. You did not. You were supposed to. You didn't at all. Ah, man, you were supposed to. You did the compressibility one, right? You did the tank and flow out of the tank was choked. And then, okay, so you did that one, but you didn't do the power law one? Okay, oh man. Alrighty, well, so the lab I thought you were doing was one where you take a pipe and you measure the pressure drop across the pipe like this, right? Okay. And if flow is laminar, then the pressure drop across that section of the pipe will be described by, okay, so if flow is laminar, the pressure drop will be described by 4K L over D 8 3n plus 1 over pi n d cubed over n b dot n. And so you can just use a pipe in order to figure out what k and n are. And normal way to do it is you take the natural log of both sides of this, and so then the n is the slope. I am not gonna ask you to do that on the final. I want you to know that you can do it. What I would ask you to do on the final is that I say this is a power law fluid, and then you have to figure out what's the pressure drop in it, and then other things like what's the power of the pump, all that other stuff you know if you know the pressure drop. So what you would need to do is figure out whether it's laminar or turbulent, because in laminar, you could use that for the pressure drop, which, and then for turbulent, this is this, okay. So for laminar, you can use that, or you could also use F L over D, 1/2 rho F L over D V squared like that, where F is equal to what?
Would this be either the
What's
Holland
F
or the
always
Colebrook equation? Oh, no, this is
Not the
64
Holland
over
or the
Reynolds
Colebrook,
number.
this is laminar
This is
flow.
64 divided by the
Reynolds
power law
number.
Reynolds number.
Yeah.
Yep. We've done a lot less laminar flow problems Then turbulent, for one reason, because in life, flow is usually turbulent. Though in non-Newtonian flow, it's more likely to be laminar than in Newtonian flow. Like that. And then turbulent flow, you would just do like that, where F would be so this should work for power law fluids and round pipes. So this, and the Reynolds number power law. Like this. So I would, and then the critical Reynolds number, which I already wrote down earlier, but we'll do it again, would be like that. So I would write all of these down, just all of these equations, and have them. Of everything we cover in class, I feel like, well, the compressible flow is also just like a bunch of equations, but I don't really need to do these. But this is the only topic where, to me, it just feels like a big list of equations. But one thing I want you to know to get out of this is just to know that if flow is non-Newtonian, then all of this stuff like the relationship between the friction factor and Reynolds number and how the Reynolds number is defined and all of that thing is going to change. And it will change depending on what kind of non-Newtonian fluid it is. This power law model is just one example. Okay, Connor.
Sorry, I think I just actually hit the unmute button.
Okay. Oh yeah, I just saw your box go yellow, but you didn't make any sound. So that is non-Newtonian flow. I feel like we spent a lot of time on that. It is an interesting problem. Let's go back to more general things. And we're just sort of going around, we're skipping around topics. Does anyone have a topic they would like to talk about next? Otherwise, I'll just sort of go back to fluid statics and we'll go through the class in order.
Can we talk a little bit about cavitation?
Cavitation, let's talk about cavitation. So to go back a little bit, let's talk about pipe flow. Okay. So when there's flow in a pipe, friction at the walls, So friction at the walls, what is friction at the walls caused by?
Viscous forces?
Caused by viscous forces. And I like to think about that as, once upon a time, I made you do this. And I said, see, when you rub against something shear, it creates friction. You can feel that. So friction at the walls caused by shear forces. Energy is lost. Pressure drops. Okay. And then also, okay, pressure drops according to that same equation I wrote for the non-Newtonian fluids. Or for laminar, F is equal to 64 over RE for round pipe. And for turbulent, you could get F from Colebrook or Holland. What's the difference between the Colebrook equation and the Holland equation?
The Colebrook is a little bit more accurate, but you have to solve it iteratively, whereas the
Yep.
Holland can solve it explicitly, but there's some error.
Yes, so the Holland is an approximation of the Colebrook. Okay, so that is loss across there. P1 being greater than P2, which means having a bigger pressure at the front drives flow through pipe. So the bigger pressure at the beginning of the pipe pushes it through. So a pump what physically does the pump do to the fluid that's going through there?
It increases the pressure.
It increases the pressure. So the pump adds pressure to the fluid. Okay. So that's how the pump drives the fluid through this pipe.
Does it affect the overall flow rate? Does it increase the overall flow rate at all?
Well, simple answer, yes. More complicated answer is that, again, if it's a horizontal pipe, so there's no gravity driving the flow, or then the pressure difference is what makes there be any flow at all. And also, if you look here, you can see that a greater flow rate means more pressure loss, which means you need to add more pressure. And then also the pump is going to be adding pressure and moving it through. So the pressure it's adding increases the flow rate. They're not really independent. I guess that is why it took me a second to figure out how to answer that question. But you know what shows us exactly what this is, how this works, is a pump curve. Okay, so the pump curve would be like pump head, which, if you'll recall, pump head is the pressure added by the pump over rho g versus the flow rate. And on your typical pump curve pipe, we're going to see two curves. One of those curves comes from your pipe system. It comes from the mechanical energy balance for a pipe system, which would be delta P. This is sort of the overall pressure difference from point 1 to point 2. So like, I'm just going to draw one representative thing for fun. So like we have a tank like this, and here's point 1, here's point 2, and here's a pump. Let's say that. Okay, delta P overall over rho g plus 1/2 delta alpha v squared plus delta z is equal to the pump head minus the head loss, like that. Okay, so if you took this equation and you solved it for the pump head, you would get a function of the flow rate through the pipe. Why? What in this equation changes with the flow rate through your pipe?
Velocity.
The velocity, which will change this a little bit, but more importantly, it will change the head loss. Right? Okay, so the more flow you have through the pipe, the more head loss you have. So with more flow, do you think we're going to need more pump head or less pump head?
More pump head for more flow?
Connor, repeat that, please.
More pump head for more flow?
More pump head for more flow. Okay, so we're talking about the point of view of the pipes. The more flow you get, the more friction loss you get, and so you're going to need more pump head in order to push the fluid through and overcome that loss. So that means that the curve that comes from the mechanical energy balance on the pipe system is going to curve up like this. System curve. It's called the system curve. And it's from the mechanical energy equation on pipe network. Okay. So now we think about the pump. So that is one of the curves. And then the other curve comes from the pump. And we can think about it this way. The pump usually has some kind of shaft that's spinning around, and it's pushing the fluid around and around, and it's adding energy to it. And that energy can either go, well, it will go into both, but it sort of can either go into increasing the pressure or moving a bigger mass flow rate of the fluid through. And so that means that normally the more pressure rise the pump provides, so the more head the pump provides, usually the less flow rate it will provide. And so it curves down, that curve curves down like that. And you call this the performance curve. The pump performance curve. So it tells you what the pump will do. Okay? So the line going up, that comes from the pipe network, that says the head you need. The line that curves down, that comes from the pump, and it says this is how much head the pump will give. And generally, higher flow rates means less head given from the pump, and vice versa.
Hey, Dr. Nickerson.
And it is determined experimentally. Yes.
Quick question. Why do we not put the system curve starting at 0, 0?
Okay, so it will depend on the situation, but so the system curve comes from, if you solve this like this, it would be like plus the head loss like that. Okay, so look at this and look at that. That means, so the pump head it does have to overcome the loss, and that's the main reason why it curves up like that as you get more flow. But it also needs to, if you are lifting the fluid up, like in this example I drew, it has to do that. So delta Z will raise it up. And then if you are changing the pressure, so like if you're going from a gas at atmospheric pressure to a pressurized gas tank, for example, or in nuclear power plants, water has to be pressurized in order to keep it from vaporizing. So you could have a pump that is taking water and it is at atmospheric pressure, and it is running it to a tank at a really high pressure. So if you're changing the overall pressure or you're changing the height, that's also going to change how much pump curve you need. And if we look at this equation, we'll see that for a given system, those things are constant, and they'll just raise the equation up like that. So if you had a situation where the overall delta Z doesn't change and the overall pressure doesn't change, then the curve would start at 0. But if it doesn't, and so then if what I'm calling point 2, the second point, goes, if that's lifted higher, what happens to the curve?
It would shift up.
It would shift up like that. Okay. And so what will that do to the operating point, which is what your system is going to actually do? Like when you hook a particular pump to a particular pipe network, what will actually happen is the operating point. That is the pump head and the flow rate you will get, which means that, okay, so if that delta C changes, the system curve gets shifted up, which means that now you need more pump head. And so what will happen to the flow rate?
The flow rate will decrease.
The flow rate will decrease. Okay. And in fact, people can use this deliberately in order to decrease the flow rate. So let's say you have a valve, right? Let's say you have a pipe with a valve in it. What will the valve do to the loss, the head loss in this system?
It will increase, right?
Yeah, it creates a minor loss. So the head loss associated with a valve or with a minor loss would be KL B squared over 2G. All right. Okay, so it creates a loss. So if you have lots of things like bends and fittings and valves and stuff, it will create minor losses, which will make this pump curve, it would make it curve up more like this. And so the more minor losses you have, your flow rate will go down, right? Everyone see that? Okay, so what that means, and so which do you think would cause more of a minor loss? A valve that's totally open or one that's like half closed?
Half closed for sure.
Half closed. So if you like half close the valve, or depending how closed it is, you'll get more or less loss. Partially closing valve increases loss. So if it increases the loss, what will happen to the flow rate you'll get?
It'll decrease.
It'll decrease because it'll, so partially closing the valve will increase the loss you get at any flow rate, which will make the curve look like this, and then the operating point will shift over to the left, and you'll get less flow rate. So what people do a lot of times is they put valves in their pipeline, and they want a valve that has as little loss as possible when it's totally open, and then they can close it in order to control what the flow rate actually is. And so they can actually just sort of tweak how much they close it until they get the flow rate they want.
So quick question about that.
Yep.
So when you lower the flow rate, does that not increase the electricity that the pump draws now?
So probably, it will depend, because the pump power is the delta P provided by the pump times the flow rate, or the mass flow rate times gravity times the pump head. Okay, and so you lower the flow rate, and so lowering the flow rate will reduce the amount of power you need, but lowering the flow rate also increases the pump head you need on these, which you can see from the pump curve graph. And so increasing the pressure, the pump head will increase the power, decreasing the flow rate will decrease it. I hope I said those two things right. Lowering the flow rate decreases power, increasing the pressure drop increases power. Those two things are related, and so I'm not sure you can say exactly what will happen. In fact, I think the power curves, I think they usually look like this. Like they go up and then down is what so yeah. Yes, I think they usually go up and down, so it will depend on what the curve is exactly and where you are in the curve exactly what will happen.
Well, and even with all that complications, it depends on the efficiency point, right?
Yep, and it also depends on the efficiency, because there are losses inside the pump, and you don't, so this is power needed by the pipe system, is what this is. But in the pump, there's going to be losses, and the pump is going to need more electricity than it's going to put into the fluid. Well, it's going to need more power from electricity than the power it puts into the fluid. Okay, and so the efficiency will be the power pump, which again is the power it puts into the fluid, over the power, call it the power electric, which is the power that the pump draws. So if you actually want to know how much power the pump uses, like what your electricity bill will be, like that. And the efficiency also just changes with, again, this is something you'd have to measure, and it also changes across here. There's a couple different ways this can be drawn. I showed you some examples of pump curves that showed efficiency curves as sort of lines like this, where this line represents 50% efficiency, but usually it looks something like this. So the efficiency also changes with the flow point, with the flow rate.
Dr. Nickerson?
Yes.
Going back to your previous discussion about shifting required curve, system curve, is there nothing that we can do with the pump performance curve to adjust flow rate?
So not really. There you can have a different model of a pump, or you can have the same model, and a lot of times the same model will have different sizes of impellers inside of it, because again, a centrifugal pump, it has impellers that are spinning around inside of it. So you can order the same model with different impeller sizes. I don't think people normally switch them out. I think you just buy it one way or another. So the only thing you can really do to change your pump curve is to get a different pump, or to change your pump performance curve is get a different pump.
Okay, so it'll be in jumps rather than like you being able to, like with a valve, you can like kind of.
Yeah. Well, the valve would be in the pipes. So oftentimes you put a valve on the going out of a pump, but that doesn't change the pump performance curve. And in fact, that's how they find the pump performance curve, right? So you have a valve going out, and they'll close the valve all the way, and that will give them the maximum pressure it can do, right? So there's no flow going through, and it'll just raise the pressure. And then they'll open the valve all the way and just have and you don't have anything, including no significant pipes with losses, and that will give you the maximum flow rate you could get out. And then you can use the valve to change where on this curve you're going to be, but it won't change what the curve is. So the valve is changing the system curve again, and that shifts you up and down around the pump performance curve, but the pump performance curve is just set for the pump you have. Okay. So that was a long preamble to get to Mara's actual question, which was about cavitation, that I figured we should review all of this because cavitation also relates to how pumps work. Okay, so now let's talk about cavitation. Mara, do you remember what the definition of cavitation is, what it actually is?
From what I understand, it's when the pressure inside of a pipe either gets lower than or greater than vapor pressure, so that it starts to evaporate.
It starts to evaporate. So it gets lower than vapor pressure. That's what vapor pressure means. So the vapor pressure is, you have a liquid, right? And pressure is pushing on that liquid, keeping it a liquid. So there's these molecules inside the liquid, and pressure pushes those molecules to stay inside the liquid. And when the pressure on the liquid gets lower, some of those molecules will pop out and be gas, right? So lower pressure means you're more likely to vaporize. Because again, higher pressure pushes the molecules down into the liquid, lower pressure, the molecules can pop out and be a gas. Okay. And so that means that so the vapor pressure tells you that if you get lower than the vapor pressure, you're going to vaporize. That's what the vapor pressure does. You'll learn more about it in thermo. But that's how you can remember that low pressures make vaporization, make cavitation. So pressure lower than vapor pressure, liquid vaporizes. Some of it will turn into gas. So the liquid vaporizes, which means that, I'm going to draw this. Okay, some of the liquid vaporizes. And if some of the liquid is vaporizing, bubbles form. So that now there's bubbles. So now there are bubbles inside our liquid, and then the bubbles collapse. Basically, any increase in pressure or disturbance will make the bubbles collapse. And when the bubbles collapse, that creates a shock wave. Going through the liquid. We did not talk about shock waves in the compressible flow unit. If you are interested in shock waves, there's some stuff in the book in the compressible flow chapter. But just know a shock wave can happen when the bubbles collapse, which means there's this sort of wave of changing pressure. And the shock wave damages equipment. So pressure lower than vapor pressure, bubbles form, bubbles collapse, creates a shock wave damages the equipment. I showed you some pictures of like pump blades that had little holes in them. That's caused by cavitation. Okay, sounds kind of like popcorn popping. Okay, so you can tell that cavitation is happening if you hear this sound. I showed you a video. You can look up other videos if you are curious about what it sounds like, but it's sort of like a sound. Okay. That damages equipment. So that is theoretically what cavitation is, and so that's why we don't want it. Okay. So cavitation happens when pressure gets too low. And now let's look again at our system. So we've got a 0.1 and a 0.2, and this is a pump. So cavitation happens if pressure gets too low, and inside the pump, pressure can also get lower because it's, again, the water or the liquid is getting swirled around in there. So somewhere inside the pump, pressure can get lower. So even if cavitation doesn't happen in the pipe, it can happen inside the pump, and that's bad. We want to prevent cavitation. So let's think about it this way. I'm not going to call it 0.1 and 0.2 anymore. I'm going to call it let's call this 0.1. 0.2 is right before the pump. 0.3 is right after the pump. 0.4 is here. And let's pretend we start at P atmosphere for both. We start and end at P atmosphere, which is a pretty normal situation. Okay, so if we start and we end in P atmosphere, where will the highest pressure in this pipeline be?
0.3.
3, says Zach. Why? Because that's what the pump does. It adds pressure. We said that. Highest pressure in pipeline. So after the pump, you get a really high pressure and it pushes the fluid through the rest of the pipe. Where will the lowest pressure in this pipeline be?
Right before the pump.
Right before the pump.
Is the pump somehow, is it like, if the velocity was 1, or if it was 0 at 0.1, could the pump still be pulling fluid from the point?
Yes, it can.
Is it creating like a vacuum then?
Yes, it can, and I will show you how. So I just drew this as theoretical things, but a more realistic situation is we have some tank right like this, like a tank of water, and here's some other tank. I'll just draw them the same size for now. And you're moving the water from that tank to that tank. And so when we did our mechanical energy balance, we would usually like to put those as our points, but let's say point 1, 2, 3, and 4, just like I drew there. Okay, so the velocity at the surface of a big pool of water we say is 0. And in reality, it isn't exactly 0, because in reality, in this case, the first tank, the water level's dropping, right? And so the velocity is going down. And in the other tank, the second one, the water level is going up. And so technically, there is a velocity at that surface, but because the surface is so big, then it's dropping really, really slowly compared to, and all the other, so the energy from everything else is going to just be really big. And so we just say it's about 0. We make that assumption all the time. But, so in this case, we would say point 1 and point 4 both have velocities of 0, but there has to be a velocity going through the pipe or else it wouldn't be moving from the first tank to the second tank, right? Okay, so yes, so the velocity at point 1 can be 0, and then there is some V2 is equal to V in pipe. And so is V2 and V3 if it's a constant diameter pipe. That's that velocity there. And that's that velocity that causes the loss. That's the velocity we would use when we were calculating the head loss. So that's why even if the point 1 and the point, I called it 4, we drew here on our mechanical energy balance, both have a velocity of 0, there's some velocity in between that causes a head loss. And there's going to be a velocity going into the pump. Does that, I feel like your eyes still look skeptical. Do you have a question about that? Okay, cool. Alrighty, so point 2, going into the pump will be the lowest pressure on the pipeline. We know this has to be because the pressure is dropping as we go along. So what is physically happening there is that the pump creates a high pressure going out, and then going into the pump creates suction. So the pump creates a low pressure going in and a high pressure going out. And so after the pump, the high pressure pushes the water through, and then before the pump, the suction pulls the water in. That's what's physically happening. Okay. So that means, but what that means, yeah.
Sorry, so can we think of it like the pressure drop is causing the velocity to increase until you get there, and then you get rid of the pressure drop, and then the velocity stays constant? Or is that not a good way to think of it? Well, I guess like if there wasn't a pump, because if your pressure is going down by the mechanical energy balance, oh, I guess that has to do with the head loss. Okay, it doesn't really affect the velocity.
Yeah, that has to do with
that
the
makes
loss.
sense.
So yeah,
All
exactly. Right. But you are right to think about how the energy is changing around, but there's also those losses in there. Okay.
All right, thanks.
All right. Okay. So the pressure will be lowest going into the pump. And remember, we also said that cavitation, so if there's cavitation anywhere in the pipeline, it will be in this pipe before it gets to the pump. But the pressure can also get lower at some point inside of the pump. Okay. So what that means is that if the pressure going into the pump is too low, then if it drops any lower when it's inside the pump, then there will be cavitation and the pump will be damaged. And Mara, you're the one who asked about cavitation. Does that make sense?
Yeah, that does. I think one of the
so
biggest
the lower
things.
pressure or the lower head we have going into the pump means the more likely there's going to be cavitation inside the pump. And so we want, and so that is why we define the notion of net positive suction head. Net positive suction head. And the net positive suction head is defined like this. It is defined as the pressure head going at plus the velocity head going into the pump minus the vapor pressure. That is how the net positive suction head is defined. So this tells us that this is the pressure head plus the velocity head. It tells us how much energy we have going into the pump. It is the stagnation pressure, which means that if the velocity goes to 0 somewhere, that's what the pressure will be. But it's the stagnation pressure, which means it's the sort of the energy from the pressure plus the energy from the kinetic energy. Right, and then, so that's the head we have going into the pump, and then you subtract the vapor pressure. So this tells us, oh, I said vapor pressure, but it should be vapor pressure head. It should be, we want this all to be in the same units, the same dimensions, like that. Okay, so it subtracts that vapor pressure head, which is why this gives us net head, right? Because, so why do you think we subtract that vapor pressure head there?
To find how many feet above, well, to find how many AS meters, inches, feet, the height above the vapor pressure, so that if it's negative, we know that's below vapor pressure. If it's positive, it's above.
Yeah. So yes, that is true. But it is not negative and positive that's important here, because this tells us going in to the pump. This tells us how much head we have. So minus PV over rho G says this is how much more head we have than the vapor pressure heads. So this tells us how much more pressure we have than the vapor pressure. And that tells us how much room we have in order for the pressure to drop lower. So it's not necessarily, we don't care about 0 that much. What we care about is that inside the pump, the pressure will drop some more. And if it ever drops into vapor pressure inside the pump, it will cavitate. So this tells us how much room we have, how much head we have above what it would take to not cavitate. So this is the difference between essentially the vapor pressure will cavitate and the pressure we have going into the pump, because inside the pump it's going to drop some and that would cause cavitation. Okay. And right. And you can get, and so a lot of times we don't want to have to do a mechanical energy balance between 0.1 and 0.2 to figure out what P and V going into the pump are. So you can rearrange So you can take the mechanical energy balance, which goes like that. And so this is the balance in between point 1, which is our first point, and what I'm calling point 2, which is going into the pump. So write it like this. And so this would be P2 and this would be V2. These right there. And what we can do is we can rearrange this so we get P2 over rho G plus V2 squared over 2G. So that's at the pump inlet. Is equal to, and we would just do this, so it would be P1 over rho G plus 1/2 G V1 squared plus Z1 minus Z2, like that, minus the head loss, like that. So that's just the mechanical energy balance for 1 and 2, and I just solved it like that. And so that's what that is, and now I just subtract the vapor pressure to get the net positive section head. There we go, like that. Yes, so Rankin asked, this would be NPSH available, and yes. So this would be, let's call it avail. So this is what we would call NPSH available sometimes, or sometimes you'll just say this is what the net positive section head is. Net positive section head available, because this says this is the energy, this is the head that is available from this pipe system. That is what that says. And if we drew it on a graph, that graph would look like, so looking at this, so this would be head in units of feet or meters or whatever, and this would be flow rate, just like with the other pump curves. So look at this equation I just drew. If there's more flow rate going through our pipe, what will that do to the head loss?
It'll increase it.
You get, oh, what did you say, Rankin?
It'll increase the head loss.
It will increase the head loss. More flow rate means more head loss. Okay, and so I look at this equation and I say, if there's more head loss, will we have more net positive section head available or less net positive section head available?
Less.
Less, and Sarah, I saw you say less silently with your lips, so good for you too. All right, and so, and what that means is that just the more head loss there is, the more energy is lost before we get to the more energy, the more pressure is lost before we get to the pump, which means the lower pressure it will be going in, and if the pressure drops at all inside the pump, it will be more likely to cavitate. And so therefore, that head, that curve is going to curve down. Curves down like this, because more flow rate, more head loss, less head available. That is the NPSH required curve. Comes from mechanical energy balance on pipe before
Isn't
pump.
that the available, not the required?
It is available, and I wrote required. Thank you. Okay. All right, but now we also need the required curve. So the required curve comes from the pump. And the higher the flow rate is going through the pump, the more pressure it's gonna need in order to not cavitate. It's a general rule. And so the NPSH required curve curves up and it looks like that. Comes from pump, measured experimentally. Okay. So the NPSH available, this comes from the mechanical energy balance in the pipe before the pump, and it says this is how much pressure, how much energy I have going into the pump. And the required says this is how much head I need going into the pump for there to be no cavitation inside the pump. Okay. And so when they cross over, what that tells us is okay, like that. So in this whole, after that point where they crop over, cavitation, what are you doing? Okay, cavitation will happen after that. Give me a second, I need to plug this in. I will be right back. Okay, so let's see. All right, so that gives us to the end of cavitation though. All right, so Mara, you were asking about cavitation. What I want you to know is that that place where those pump curves intersect, that gets you the minimum flow rate you can have without there being cavitation. And if you have more flow rate than that, there will be cavitation. That's what I want you to know. Do you understand that, or is there anything more about that that you want to know about?
Yeah, so that makes sense, and that was very helpful. There's like one question I have left, basically just on the trends. I think there's like three major trends with NPSH, and which is also cavitation. So as like the pump, if the height of the pump above the original, like the 0.1, if that increases, then NPSH is going to decrease, right? Okay. And
Yes.
then if V dot increases, that means head loss increases, so NPSH decreases. And then this is like the biggest one for me. as temperature decreases, pressure in the pipe is going to decrease. So does that increase cavitation likelihood?
Oh, so you are, okay, let's look back at that equation again. So you are right that you are correct. Well, for a gas, the temperature in the pipe is going to increase pressure because of the ideal gas. Like, so think of the ideal gas law. A gas at a higher temperature is going to have a higher pressure. So if there was gas, you could say a higher temperature means a higher pressure in the pipe. But for a liquid, it doesn't really mean that, because it's sort of true that a higher temperature usually makes a liquid expand, which would slightly increase pressure, but it's just not a big effect, and we would ignore that. Okay. And cavitation is when the liquid turns into a vapor, right? And so it's not something we would worry about if we were pumping a gas. So that temperature, that's not really a thing. But you are right that temperature affects this, okay? It isn't the pressure of the water in the pipe that temperature changes. What temperature changes is the vapor pressure. Temperature changes the vapor pressure. And remember, the vapor pressure says if I get lower than this pressure, then I'm going to vaporize, right? And so if I get lower than this pressure, I'm going to vaporize. And do you think that at a higher temperature, it's easier to vaporize or less easy to vaporize?
It would make it easier.
It would make it easier. So remember, pressure is pushing the molecules down into the liquid. And so a higher temperature means the molecules are moving faster and they can punch through and move. What that means is that, so higher temperature means easier to vaporize, means a higher vapor pressure. Higher temperature, higher vapor pressure, because that means that there's more pressures that are below the vapor pressure, and it will be easier for the liquid to vaporize. Okay. Higher temperature, higher vapor pressure, easier to vaporize. All right. And if we look at this equation, we will see that a bigger vapor pressure means a smaller net positive suction head. And in this case, what changed it? So all of these things change the amount of energy you have going into the pump, because they change what's happening in that pipe going into the pump. And so all of those things will change that. What the temperature does is it makes a bigger vapor pressure, a higher vapor pressure. And so then the difference between this part, the head you have going in, and this part, the vapor pressure, will be smaller. And therefore, it will be more likely to cavitate. And therefore, you will get less net positive suction head available, and it will be more likely to cavitate. So that is what happens with the temperature. The temperature increases the vapor pressure, which decreases the net positive suction head. And theoretically, what's happening is that the temperature makes it easier to vaporize. So now you need more head in order to not cavitate. That's what temperature does.
So like on a cold day, cavitation would be less likely.
Less likely, yep. Because on a cold day, it is harder for the liquid to vaporize. on a cold day, or if it's a really cold liquid. And in fact, often the net positive suction head available curves are for a certain temperature, because it will, the temperature will change what happens inside the pump, and so it will change the net positive suction head required as well. So if you, the NPSH required curve, that can also change with temperature, and so when you get the curve from the pump manufacturer, it will often be for a certain temperature. And so if you were trying to pump like really hot liquid near the boiling point, you would want a net positive suction head required curve for that temperature. That's not as big though. The main thing that temperature does is it changes this, and it means you have less net positive suction head available.
Dr. Nickerson?
Yes.
What will the format of an NPSH required look like?
Okay, so that's available. This is required. Required curves up. Available curves down, required curves up.
Will you given like an equation?
Yes, so you'd be given an equation. Because it comes experimentally from the pump, just like the pump performance curve. So on tests, I'd give you an equation. In real life, manufacturers could give you an equation, they could give you a curve. Nowadays, they often have they have software that does it, but in life, they could give you just a graph with the curve on it, or they could give you an equation like this. See, so this is an example of something you might get from the pump manufacturer, and you see it just has the required curve on it. On tests, I usually give you equations, but what that equation would be is it would be what that curve is. All right. So that is cavitation. That is net positive suction head. Okay. Now I would like to talk about pressure, I would like to talk about fluid statics, so pressure changing with depth, and fluid forces. Is everyone cool with us talking about that next? Cool. All right, that's what we're going to do. And I'm just going to keep going, by the way. I said 2 hours to schedule this, but I don't have anything else today. So I will keep going. People can stay if they want. Let's talk about fluid statics. Okay. Now, the most simple thing in fluid statics is just that the pressure caused by static fluid is P equals P naught plus rho GH. You probably learned that in high school, right? Okay. And the H is just the depth we are in whatever the fluid is. And P naught would be the pressure at the top of the fluid. So, but this equation makes an assumption. What is that assumption?
Density is constant?
Density is constant. This equation assumes that density is constant. And so, and so that is why, well, that's one reason why we, instead of using that form of that pressure at depth equation you're so familiar with, we use this differential form of how pressure changes with depth in a fluid. And by now, you should have seen basically this pop up from the Navier-Stokes equation when you simplify it down many times. It's just sort of fun. Okay. So now this equation will tell us Yeah, so this equation tells us how pressure changes with depth going up and down. And if we assume that density is constant, you can integrate this and apply the boundary conditions, and you get this. P is equal to P naught minus rho GZ. This equation is actually the same equation as P naught plus rho GHY.
Because if we plug in, or having like the surface of the liquid being 0 and then going down being negative, at a height of like negative h, then plugging that in, it would make it a positive rho gh.
So this equation right here tells us what the pressure is if Z is equal to 0 at the top of wherever we are. And density is constant. Okay? And so if you put in negative h for Z, you get P naught plus rho GH. But this equation just lets us do it with Z as a variable, which is going to help us when we do things like find pressure forces, stuff like that. So that's where that comes from. But what if the density is changing?
Then when we integrate it, we have to put that on the density side and integrate it as a function of height.
So if the density is changing, then back here, then you have to put in your formula for how density is changing before you integrate it. And that formula, it could be relatively simple. So for example, here I said there's some kind of slurry, and so it's a liquid with a bunch of grainy particles in it. And more particles will settle near the bottom, and so it's going to be more dense near the bottom than near the top. And I said that you can say that the density changes with Z. And so in that case, what you would do is you would take this function of density with Z, and you would put it in for the density here before you integrate it. But remember that the most common way for density to change is if it's a gas. Because if it's a gas, then density changes with pressure. And so if you have some formula for density changing with Z, you have to put it in here before you integrate. But if you have some formula for density changing with pressure, you got to do the same thing. Okay? And that is why we had the homework problem where we found a formula for density changing with height for air. And it was, let's see. Okay. Okay, here we go. So this was for a homework problem, and what the homework was, I'm pulling this up because my pad died, so I cannot show you. I cannot draw out a problem for you, but I want to show you how you would do this. So this problem said, derive an expression for P as a function of Z in static air with the Z-axis pointing upward so that Z equals 0 at the ground, and P naught means the pressure on the ground, okay? And we're going to treat density as changeable. And the way we treat it as changeable is using the ideal gas law. So that's what we're doing there. And so I said density is equal to NP over RT. What is the M there, by the way? Sarah, I saw your mouth move. molecular weight. So this is molecular weight. Okay, so the density is changing with P. And so if it's changing with P and we're going to do an integral of P, we got to plug that in before we integrate. So we do that, and then we integrate. And I integrated from Z equals 0, where P is equal to P naught. So again, this is the pressure at ground level to some P and Z. And I got this, and I found this equation for how pressure is changing with height. And the chat asks, the review is recorded. Yes, it is. The review is recorded. All right. And I'm glad, because I really hope this is the stuff we talked about way at the beginning. So I bet a lot of people forgot this stuff. So I really hope you go over and review this stuff. Okay. Pressure is changing with height. And then I also told you what if temperature is changing with height. And so then you had to put in that formula before you integrated to. It's the same principle. If you are integrating dP, dZ, and anything in the equation changes according to either P or Z, then you have to put that function in before you integrate, because that's what integration does. It takes into account how all of these stuff is changing related to each other. So that is how you find pressure with variable density. Any questions there? All right, so then we talked about pressure forces. That is what we talked about next. There's a few other things like pressure at the same depth in a fluid, the pressure is always going to be the same. That was something we learned that's kind of a good thing to know. All right, pressure forces. Actually, let's go back there. Okay, just a couple other things to know about pressure. In the same fluid, if you're at the same depth, pressure is always going to be the same, because that's all pressure depends on, right? P is equal to P naught plus rho GH. So pressure is always the same everywhere at the same height in the same fluid. Okay. And it doesn't depend on, for example, if it's in a container, shape of the container doesn't matter. If it's at the same height, it will still be the same pressure. So for example, in these two containers, the pressure at the bottom is the same because they have the same height of water above them. And we learned about manometers, pressure measurement devices, where you use rho GH of whatever fluid's in your manometer to get you difference in pressure between here and here. So that's how you can measure the difference in pressure between 2 points, is that it will be rho GH of this height. Okay. All right, then we learned about pressure forces. And we learned, so pressure is always acting in every direction, pointing down, in like this. So pressure is pushing it in from all directions, but this creates a net pressure normal to the surface. And when we talked about momentum balances recently, we talked about the pressure forces on a control volume, right? And so the pressure forces are always pointing in at the surface of that control volume, and it is the same with solid surfaces. So pressure forces are going to be pointing in, pressing in, normal to the surface. Always normal to the surface like that. Okay. And if we're talking about the pressure like on the floor right here, then the pressure is constant at the bottom, right? And so you can just take whatever that pressure is and multiply it by area and you get a force, and it's pretty straightforward. Assuming you all understand that. But then what happens if we have a vertical surface? If you have a vertical surface, pressure isn't constant. And so what would you multiply by the area to get the force? So because pressure is changing, we have to integrate in order to get the force on the surface. Okay? So that is why we have to integrate, because of that. And so we have to use this differential thing. And just to skip ahead, we went through what you would do if it was a rectangular wall. And I said you slice the wall up into these rectangles, and each of the rectangles has an area, make that dz, and it has a width. And then you take the net pressure. So P atmosphere is going to be pushing into the right on this wall, and then the pressure from the water is going to be pushing into the left. And that pressure from the water is P atmosphere plus minus rho gz. And so the P atmosphere part canceled out, and we just had rho gz. And what we end up with is this equation for the pressure force on a vertical rectangular wall. And so you can go ahead and just write this down. And the thing to remember about this, if you write it down, is 1, this assumes constant density. 2, this is for a rectangle. And 3, this is for if there's pressure on both sides, so pressure cancels out, or there's atmospheric pressure, sorry. This says that there is atmospheric pressure on both sides, so the atmospheric pressure cancels out, is what this says. Okay. So those are things to remember about just using this guy. So that means that if it is not a rectangle, or if density is changing, then you would want to do the and on the homework, we had a couple different situations where it was changing. Gonna pull that up. Okay. Okay. So we did this one with a car underwater. And so what's happening here is the car is underwater, and inside the car, there's air at P atmosphere. And what that does, okay. That's different. Where is it? Okay, here we go. This is the car underwater. And so the car door is a rectangle, but the pressure at the top of the door isn't P atmosphere, it is, so P naught would not be P atmosphere now. Instead, P naught is P atmosphere plus rho GH, where H is this depth underwater. Okay. So that means that P atmosphere cancels out on both sides, but this rho GD doesn't. And so rho GH over 2 plus rho GD. So this is the pressure that comes from being 10 feet under, is rho GD. And then I added 1/2 rho GH, and that's the pressure that comes from going down across the rectangle, and multiplied it by the area to get the force. So, and then there was another problem where we had not a rectangle. And in this case, this problem was this dam, which is a trapezoid. And I gave you the width at the bottom and the width at the top. So now the pressure, so now now it's not a rectangle anymore. And what I did was P naught acts on both sides, so pressure is just negative rho GZ. W changes with Z. So this is S for surface, but you could also call that A for area. So that means that the area of that sort of thin differential rectangle is W dZ. And since W is changing with Z, you got to put that in before you integrate. And so I found this equation for the width of the dam, which is a trapezoid, function of Z. So negative rho G times Z, so that's the pressure, times this equation, which gives you the width of the function of Z, dZ, and then I integrated and I got this. So I do want you to have this written down for the force on a rectangular wall, because a lot of times we're interested in rectangular walls and you can just use it. But know that if it's not a rectangle, or if density isn't constant, you can't use it. Or if there's some extra pressure at the top besides atmospheric pressure, then you would have to adjust it for that. Any questions about these pressure forces before we go on? Okay. Alrighty. We then talked about buoyancy, and the reason we talked about buoyancy at the same time as this is what buoyancy comes from is the pressure force. You stick some object into water or into a fluid, and there's a pressure force on it on all sides. And that pressure force, if you add it up all over, turns into a force going up. Well, yeah, it turns into a force going up, which is the buoyant force. We know that force is going up because if there was water there, that's the force that's holding that water up in that position. Okay. So the buoyant force goes up. It comes from the pressure forces of the fluid on the object, and the buoyant force is equal to the weight of the displaced fluid. Again, this is a high school thing you should have learned in high school. We went a little bit deeper into where it came from, but it comes to the same thing, that the buoyant force is the weight of this displaced fluid. And so that is why if the density of your object is less than the density of the fluid, you rise up. If the density of your object is greater than the density of the fluid, you sink down. And if the density of your object is the same as the density of your fluid, you just stay equal. So that is why a bubble of air inside of water goes up. A steel ball that you drop into water drops down. A water balloon should just kind of float where you put it. There's a slight weight of the balloon that maybe would make it go down. And then if we're in the air, I have a higher density than the density of air, so here I am, down at the bottom of the air. A helium balloon has a lower density than the density of the air, so it goes up. And then like a hot air balloon, they will control, it will go up until the, The hot air balloon is the best example. So go into the water again. There are fish that can control the volume of their body. So they'll go bigger or smaller to increase or decrease their density, which will cause them to sink up or down until they're at the same density as the water at that point, and then they'll just stay there. Okay. And y'all, yeah, again, in high school physics, you should have done buoyant force problems where if there's, the buoyant force is just equal to the submerged, the density, the weight of the fluid displaced. Any questions about buoyancy? Cool. So from there, we talked about dimensional analysis, and then we talked about drag. So dimensional analysis and drag are the other topics. We've already gone over a lot of pipe and pump stuff. So would anyone want to talk about drag or dimensional analysis? We could do either right now.
It would be nice to go over drag, like external flow.
Okay, let's do drag. Let's talk about drag. And then at the end, we can talk about dimensional analysis for a few minutes as well. Drag. Okay, the flowing fluid is gonna exert this force on this body. And so drag can come from a couple different places. This is the conceptual stuff I want you to know. Drag can come from those viscous forces, sort of pulling on the surface as it flows past. And if we have a surface that's flat compared to the flow, that's where most of the drag is going to come from. It's going to come from those viscous forces dragging across the surface. It's going to come from the shear stress. And we call that friction drag. But you can also get drag from a pressure difference across a body. So in this case, we have something that's perpendicular to the direction of the flow. And that creates what's called a turbulent wake behind it. So there's flow separation at the edges. You can sort of see how the flow separates. And the flow separation means there's this turbulent wake inside here. And the turbulent wake has lower, will have lower velocity, lower pressure. It will have higher velocity, more losses, lower pressure. So the wake behind the object will have lower pressure. And then at the front of the object, the flow hits it and it will stagnate. What happens to pressure when flow hits a surface and stagnates?
It increases because it's your static pressure plus your dynamic pressure.
Yes, Zach, it increases. Because when the flow hits the solid object, it stagnates, which means its velocity goes to zero, and the kinetic energy that was in that flow turns into pressure instead. So at the front of this object, the flow hits it, stagnates, the pressure increases. At the back of this object, this turbulent wake has a lower pressure. And so that means that you have a high pressure in front, a low pressure in back, and you will get a net pressure force pushing you back. And I always tell people to imagine you're carrying like a shield or a big square thing, and the wind is, and you're trying to walk into the wind is blowing at you, it'll push you back. Whereas if you turn the other way, then it would push you forward like a sail. But we're talking about drag, so, okay. So that's the direction the drag is going to be going, opposite the direction of the flow. or actually no, in this case it would go that way, same direction as the flow. Sorry, I said that. Okay, so pressure drag, friction drag. In turbulent flow, there's gonna be, this wake will be big, and so the pressure difference will be a big deal. So in turbulent flow, and the higher Reynolds number gets, the faster we're going, the more pressure drag is going to be important. And so most of the time in life, pressure drag is going to be where most of the drag is coming from. Viscous drag is going to be more important at really low Reynolds numbers when it's laminar, when flow is really viscous and slow, or in the special case where it's like a flat surface that's parallel to the flow like this, so it's dragging along it, then you'll get more friction drag. Okay. We talked a little bit about lift because drag is just the force in the direction that's normal to the parallel with the flow, and lift is the component that's normal to the flow. So drag is what makes it hard to walk forward into the wind, and then lift is what lifts you up if you're angled the right way. We didn't talk a lot about lift because if we were mechanical engineers, we'd probably talk a bit more because they care more about airplanes. And I want you to know that why airplanes stay up, but we didn't talk about it a lot. Okay. But lift and drag come from the same thing. They're just going in different directions. And the angle that your object hits the flow will change how much lift versus how much drag you have. Streamlining is where you change the shape of the object so that it creates a smaller, there's less flow separation, and you create a smaller wake behind, which decreases the pressure drag. Right? I asked you whether streamlining in really, really low flow makes sense. And it doesn't really, because streamlining is about reducing the pressure drag, which in most cases is where most of your drag is coming from. Okay. And we can figure out how much drag we have by using the drag coefficient. So this is how the drag coefficient is defined. It's a dimensionless group. Okay. And so for different shapes, you can change the flow rate past the shape and measure the drag force on it and get what your drag coefficient is. And then what you end up with is an equation for drag coefficient as a function of Reynolds number. So the drag coefficient changes as the Reynolds number changes. And the drag coefficient changes based on the shape, because the shape is what is going to cause more or less flow separation, and you're going to get more or less wake, all of that. Okay, drag coefficient depends on Reynolds number and shape. And when Reynolds number gets high enough, the drag coefficient becomes basically constant, which is why you have a table in here that gives you drag coefficients for different shapes that you can use as long as Reynolds number is high enough. This table, I think, says if Reynolds number is greater than 10 to the 4, you can use most of them. Okay, so to find drag on an object in high Reynolds number turbulent flow, which is most of the time, you find the drag coefficient from a table for your shape. And then you take that drag coefficient and you multiply it by rho v squared root a. And what area is that?
It's the area, it's like the projected area that's normal to the flow.
Yep, that is the projected area normal to the flow. So this is the most important equation about drag because this works most of the time. Most of the situations in real life work like this because it's mostly high Reynolds number, mostly turbulent, and drag coefficient is constant, all of that stuff. So definitely know how to do that, how to find the drag on some sort of object at high Reynolds numbers. Okay, we then talked about Reynolds drag over a flat plate, because here it's a bit different because here the friction drag is the most thing. If I were you, I would not, I am going to tell you, I'm not going to ask you to actually to do a problem where you find the drag over a flat plate like this and you have to use all of these coefficients. But I do want you to conceptually know that if you had parallel flow over a plate, it would be friction drag instead of pressure drag, and you would use this coefficient of friction is what it's called instead of the drag coefficient, and you would know that the drag increases as you go along in X. So I conceptually want you to know that. So that means the longer the thing is, the faster it is, the more friction drag you have here, like that. Okay. Then drag 2, we talked about drag some more. And we learned that one thing we learned is that when you get really, really slow or really, really small, you have what's called creeping flow. And then the drag force you use this way. So again, this is not as common. It's more important for me that you know the other way, but you also should know that if you get really, really small and really, really viscous, then your drag force is not going to depend on density anymore. It's just going to depend on your viscosity. And that is creeping flow. Okay? So if you can find the drag force, you can find terminal velocity. Because terminal velocity is when the forces acting on an object all cancel out and the net force is 0. So if something is falling in a fluid or rising through the fluid, if it's a hot air balloon or a bubble or something, then you have force drag, which is sort of pointing in the direction of flow, which is the opposite of the direction the ball or whatever is moving in. You have the buoyant force, which is pointing up, and then you have the weight of the object pointing down. And if all those things are equal, then we are at terminal velocity. And when we are in air, we almost always ignore the buoyant force on this, because buoyant force in air is really small because the density of air is really small. But if you're in, almost always, but again, if we're talking about like a helium balloon in air where the buoyant force is really big compared to the air, which is why it goes up, or if you're talking about something in water where the buoyant force is bigger, then you would want to include the buoyant force in this. But regardless, terminal velocity is when the forces balance out. Okay. Any last questions on anything about drag or terminal velocity? Alrighty. So the last thing is I'm going to talk about dimensional analysis. We have covered pretty much everything from the first 2 sections of the class, and then the third one is, the third section is the test you just took. And as I said, I'm going to get those graded and back to you. I am working to get it to you tonight so that you can see it before you take the test, which will be available starting tomorrow. That's what I'm working on. I'm only like a quarter of the way through though, but it's what I'm going to do all afternoon. Okay, let's talk about dimensional analysis though. So dimensional analysis just means that we can tell some things about a system even if we don't know what the exact equations going on are, just by looking at the dimensions of things. So dimensions are things like length, force, time, and the primary dimensions that we use when we're doing fluid mechanics or mechanics are mass, length, and time. Okay? So by looking at the dimensions of things in mass, length, and time, we can answer questions about them. We talked about how all equations, when you add things together, have to be dimensionally consistent. Y'all have seen me a few times over the course of the thing. You'll see that sometimes if I'm not 100% sure I did some algebra right, I'll quickly check the units to see if it's dimensionally consistent, because if it isn't, it means I screwed something up. But that's just something you can do because equations have to be dimensionally consistent. Okay, and then we talked about scaling and ratios. So a lot of times things are going to act similar if the ratios of different values are the same, right? So an aspect ratio, for example, is the ratio of the width and length of something, and it says that they're similar in a certain way. If you put a picture on both of them, it will look the same because the ratio is the same. We talked a bit about scaling. So for example, weight scales up according to about length cubed, right? Because weight is density times volume. So if something gets bigger, then its weight will go up with the cube. But then strength, like the strength of bone, the strength of legs, usually goes up by the area. So you have a wider leg, the stronger the leg is. And so that goes up by length squared. And so what that means is this: if you have a giant like this guy, this giant, and you scale him up, his weight is gonna get bigger faster than the strength of his legs gets bigger. And at some point his legs will break. And so that is why it doesn't make sense to have giants that look exactly like people and are made of all the same stuff as people. Because once they get too big, their legs will break. So that was just illustrating some of the stuff can happen when you scale things up. And so, for example, when you take a gazelle and scale it up to be an elephant, you can't exactly scale it up. You have to make its legs thicker too. All right, and this led us into talking about dimensionless groups or ratios that tell us lots of things. The Reynolds number is one we're very, very familiar with by now. Reynolds number, love it. The Reynolds number is a ratio of inertial forces to viscous forces. That's where it comes from. That's what it is. By the way, when I interviewed for an internship as a junior in chemical engineering many years ago, they asked me in the job interview, hey, what's the Reynolds number? Tell us about it. And I told them it is the ratio of the inertial force over the viscous force, blah, 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 blah. That is where the Reynolds number comes from. Okay. And so that's why it can tell us things. That's why even if you have different liquids inside pipes and they're different diameters and different lengths and everything else, you can still say some things about how they're acting, whether it's laminar or turbulent, just by looking at the Reynolds number. And here's some other dimensionless groups that are used. We learned how to non-dimensionalize an equation by taking each of the so we pick some constants that are in our problem, and we non-dimensionalize the equation. Non-dimensionalize the equation, we get a dimensionless equation. Okay. And then the next thing we learned if you have two different systems, let's say at two different sizes, for example, and you know all of the dimensionless groups that are relevant to whatever behavior you care about, for example, drag coming from flow, then you can say that if the two systems have the same dimensionless group, they are acting the same, that means they are similar. And this is the concept behind wind tunnels. It's how they work. So you can take a really small plane, or like a 10-foot plane, and put it inside a wind tunnel, and you can use that to figure out what the drag on a really big plane would be. And the way you do that is because you have to make sure that all the dimensionless groups for both of them are the same, and then you can do it. So for example, for this specific case of drag, there's two numbers. There's the Reynolds number and the drag coefficient here are the two dimensionless groups that matter for drag on an object, which you know about now because we went through that whole unit on drag and you learned how, yeah. Anyway, Reynolds number, drag coefficient will tell you what drag is happening. So what you can do is you do a wind tunnel and you change and you have a scaled down object of some kind, and you change the velocity of that object until the Reynolds numbers are the same. And now that the Reynolds numbers are the same, you know that if the Reynolds number is the same, you know that the drag coefficients have to be the same. So then you measure the drag force on the small car and set the drag coefficient equal like this, and you can get the drag force on the big car. So that's a way of using similarity to do dimensional analysis. And you can always do that as long as you know all of the pies, all of the dimensionless groups that are important. Because if you know all of the dimensionless groups except for one, and you make them be the same between your two things, then that last one has to be the same too. Okay. And so the last thing we did is we talked, so that's what you can do if you know what dimensionless groups are. So how do you find the dimensionless groups? And I said you have to have a list of everything you care about, basically. You need all of the parameters that are relevant. So you might know, for example, that the drag force on the car depends on the density and viscosity of the fluid, and it depends on the velocity of the flow, and it depends on the size of the car, but you don't know exactly how. You just know that if you change any of those things, it'll change the force. So you list all of your parameters, you get the number of parameters, in this case it was 5, you list your primary dimensions for each of those, you figure out how many dimensions you have, in this case it's 3 because you have length, time, and mass, and so that means you expect there to be 2 pies. Okay. And so then you're going to pick your repeating parameters, which are the ones you're going to use to non-dimensionalize the rest of it. And you need at least one for each of the dimensions you have. So in this case, you need a parameter for time, mass, and length. And for length, I would just choose the length of your car, the diameter of your pipe, whatever. For mass, for fluids, usually you pick the density for the mass. That's the easiest one usually. Okay. And then for time, usually the velocity is the easiest one. Okay, so that means, so in this case, our parameters were force, drag force, density, viscosity, velocity, and length. I picked density, velocity, and length as my repeating parameters, one for mass, one for length, one for time. So that means the ones that were left over, drag force and viscosity, I'm going to non-dimensionalize those. So first I take the drag force and I figure out what I need to divide it by to cancel out all the dimensions. And I do the same thing with viscosity. And I end up with the drag coefficient and the Reynolds number. And in practical life, if there's viscosity and density and velocity and length in my problem, and I know I'm going to be non-dimensionalizing viscosity, I usually skip ahead and say the Reynolds number. Okay. So, any questions about dimensional analysis? Alrighty. So, that was good times. I'm going to put this recording online. My notes cut off because my pad died. This recording will be online. I would suggest you go over the previous exams. The exam keys for exam 1 and 2 are up, and actually right now, as I am speaking to you, I'm going to post the exam key for exam 3. Post it right now as we talk. Okay, so go over those exams in the exam key. And I would spend time on the first one, especially because all of the pipe stuff, you had the whole project and everything to remind you to make sure you remember the pipe stuff. But that first exam that had dimensional analysis and static pressure and pressure forces and Bernoulli equation problems and the drag, that exam you have probably forgotten more stuff about. So on the exam press page, I am putting exam 3 key. There you go. All right. Come by my office hours if you want to talk about anything in specific. Glad you came. Okay.
Thank you.
Thank you all.